Welcome back. I'm going to show you how you can use ChatGPT, the more modern ChatGPT, because I've shown you something similar in the past to do basic control system design, at least from an academic point of view. I'm sure that if you're in industry, you've got all the fancy software anywhere, but here things are a little bit different. In the past, you might have had to buy MATLAB or simulate things in Python, but we've got to the stage now where ChatGPT, and this is O4 Mini High I'm using at the moment, can run its own Python code within it and do its own simulation. So in the past, I'd have to tell it to do something, and it would give me some code in MATLAB or in Python. I'd take that and then I'd run it, and then I'd get the answers. And then if I wanted to change something, I'd have to, once again, I'd have to tell it to change something. It would give me more code, and then I'd take it out and so on. But now I can run it within ChatGPT. Now, that doesn't mean it's running on my computer, so don't worry, it's not actually taking over my computer. I wouldn't worry too much about it if it was actually at the present time. I'm pretty sure it won't take over my computer, but it's running it on its own server, so I'm not worried about that side of it. It's not suddenly going to design some fancy thing to take over my machine. So what I've said is, let's take an example. This is the example I'm giving here, but I don't have the fancy mathematics. I'm just typing it in terms of, the symbols. I'm just typing it in here, up at the top here, in terms of basic sort of ASCII characters. So I said, consider a transfer function given by g of s equals k over s 1 plus stm omega n squared s squared plus 2 zeta omega n s plus omega n squared. And I said, just rewrite this. So this is to make sure that it's got the right transfer function. And it's written this, it's beautified it, if you like, in the sort of LaTeX form. So this is like a motor plus load with a position output. That's the mechanical integrator, K upon S. K is the gain, which I haven't put the numbers in yet. Tm is the motor time constant. And this is the structural resonance of the rest of it, the motor plus the load. This is what makes it tricky, actually. The reason I put this in is because I've tried other examples without structural resonance, and of course they do in many textbooks, including my own textbook. But in my textbook, I normally consider this as well, the structural resonance, because in real life you do have something that limits bandwidth. You can't have a control system with something that that's got a finite, that has an infinite bandwidth, because otherwise you can just define the unity gain point, the bandwidth of the system, to be any way you like. Whereas this reduces the chances of you doing this because of the phase, and I'll just explain that in a moment what I mean by that. So here's my transfer function, and so I know now it's got the right transfer function. So that's the first thing you should do, and it's just written it like that. And it's done all this stuff. I didn't even ask it to do that. It's multiplied it out into a fourth order polynomial. I wouldn't want that, but it's done it. Now I said, now let this have parameters as follows. K equal 100, Tm equals 3.2, E minus 3, so that's 3.2 milliseconds. Omega n is 6.28 times 10 to the 3. That's going to be radians per second, because that's the undamped natural frequency, if you remember, omega n of a second order system. Zeta is the damping factor. So zeta is 0.1 I've put, so it's quite a, there's not much damping. Again, deliberate. That gives you a lot of negative phase shift. And I've just said draw the bode plot. Now, although I'm not doing this real time, I should have done really, it does this little program. Now I could take that program and run it myself on some Python environment, but I don't have to, because it's doing it itself. This is using matplotlib, so it's importing that as a library. NumPy is the number thing that it uses, that Python uses. So it's doing this numerical calculation, and not only that, it's going to plot my frequency response, and it plots it, and it's pretty much spot on. This is the example I used in my textbook anyway. This phase, by the way, is what's called wrapped phase. Nothing to do with music. It's wrapping, meaning just to get it in the graph, it's flipped by 180 degrees. So the real phase goes from about minus 100, goes here, and then it keeps going negative down the way. I actually prefer it unwrapped. Maybe I can ask it to not to unwrap it. Actually, I haven't tried that. Let's try that. Redraw the board plot, but unwrap the phase. Okay, see what it's going to do. Now you'll see it says thinking. Oh, very quick. And there's the code it's producing. Notice it's running the code at the moment. You see how it's flickering, unwrapped. And there it goes. That's how it should be. So now it's unwrapped the phase. I much prefer it like that. So we're going to design, I'm not going to ask it to design the control system, put a controller in. I'm just going to play around myself to begin with. And I'm just going to say, let's just, a naive way of controlling controlling the system might be just to, let's say, increase the gain. You can see this, we can make this frequency the unity gain to begin with. Let's see, we don't want this resonance here to go above 0 dB, otherwise you get multiple phase margins and you get oscillations at high frequencies. Actually, maybe I should illustrate that first, actually. So, okay, I'll illustrate that first to show that that's the case. Maybe I should say increase the forward path gain by 50 dB, and then that'll show you, and then simulate the system using negative feedback. Let's just do that as an example, just to show you that doesn't work. So if I can say introduce, this is how I'm going to do it, introduce a controller in cascade. I've got to specify where it is because it could be in the feedback loop. C of S equals, in this case it's just going to be K2. So I'm going to do that, and sorry, I was disturbed there by a phone call. So I introduce a controller in cascade, C of S equals K2, and it's only going to be a gain, where I'm just going to define it in dB. K2 is 50 dB. And then to begin with, I'm just going to say redraw the board plot. I'm not going to put negative feedback around it to begin with. So you can use this as a teaching aid. So whereas in the past I'd have to type in MATLAB code and go through those procedures, it's doing it itself, and it's running. It's running it. It's put its controller in, controller gain in dB. And it's inverted. I said 50 dB, so it's converted the dB version back into normal gain. Take 10 to the power of that divided by 20, and it should have now I've got it. Oh, that's nasty. So I can see that's my new board plot. It's actually a little bit that's going to be pretty horrendous. Actually, that's unstable. You can see the from here, if I consider this as the crossover frequency, it's got a phase margin of minus, well actually it's maybe minus 180. I'd say that's completely oscillatory. Just to prove that, I'm going to ask it to do the step response of the closed loop system. So plot the step response of a closed loop system using unity negative feedback. That's going to be just, pretty much just going to infinity, I think, or an oscillator, or very close to oscillation. So it's just doing as I'm telling it to do at the moment. It's not using its own, it's just acting as a tool. I see it's running this. You see the flickering. I think that's it running. I'm not sure really. And it's running. Yeah, there we go. Beautiful. And totally unstable. So now we've got to figure out a way to make it stable. And it does The sponge settles in a few minutes. So it didn't get that right, did it? The sponge settles in a few milliseconds. It's a slight overshoot. Actually, I'm going to quiz it on that and just say, is this response not unstable? So what it'll probably do is work out the roots, I suspect. That's what I've tried it before, and it normally works out the closed loop poles. Yeah, see here it's working out roots. This is another amazing thing that it does. It just it can work out the Indeed, divergence oscillations grow exponentially, confirming that the system is unstable. So it says, so it's already worked this out. So, gone are the days when you had to do what was called a Routh-Hurwitz test, although you don't need it in this case because you've got the Bode plot. But it already knows it's got two roots in the right half plane. So the closed loop poles have positive real parts, so it's unstable. But it didn't know that before. I had to kind of force it to work that out. But that's quite interesting that it's done that. So perhaps what I can do is go back to the original Bode plot and, this one here, and reduce the gain down. Actually, might not make much difference because, let's reduce the gain down. Instead of 50 dB gain, let's make the gain just 20 dB gain. Let's use K2 as 20 dB instead and redraw the Bode plot. So it's going to do the program again. I don't have to fiddle around in MATLAB, I just tell it what to do. So I'm still using my own expertise here, such as it is, because it's not telling me what to do. It's just following what I'm doing. So this is not a very good control system because I'm not making full use of the bandwidth. But you can see here at 0 dB, it's got a phase shift of minus 150 degrees. So it's got 30 degrees of phase margin. So if I tell it to do a closed loop system around this, it should be stable, but it'd be quite oscillatory, because its phase margin is only 30 degrees. So it should have something like 30% overshoot of that order. Determine and plot the closed loop step response again. But at least it won't be totally unstable like it was the last time. And off it goes. Won't take it very long. Yeah, that's so I'm going to have to ask it to. It's because I've reduced the bandwidth quite a lot. I'm going to have to tell it to increase the number of. As I said, it's not a very good control system because it's very slow because I reduced the bandwidth. Let's make the time here go up to 20 seconds. Okay, let the maximum time for the simulation be 50 seconds and repeat step response. If you make the odd spelling mistake, a typo thing, it shouldn't matter because it's very good at language. It's very easy to do that, of course. I mean, and that's something you could do very easily yourself. I'm not suggesting. Oh, there it is. It's probably too high now, so I'm going to reduce. What was it before? It was 5 seconds. Okay, we should really make it. Let's make it 15 seconds. Okay, make it make maximum time so sorry, it was 5 seconds before, wasn't it? Yeah, 5 seconds was no good. So I wonder why. Okay, let me just make it 10 seconds. And repeat closed loop system step response. You might argue this takes longer than doing it manually, of course. I'm not very sure if that's right now. I said it would have 30% overshoot. It's got 40% overshoot. But why is it different from here? And has it made a mistake? See here, by 5 seconds, it's not reached its maximum. But here, by 5 seconds, it has reached its maximum. Are you sure? Sure, this is the correct step response. Of course, I can go through here and work it out here. This is just basically MATLAB. Ah, that's more like it. What has it done? Why is it 2 left? The output quickly settles to 1 and remains there. And the zoomed in not to 10 milliseconds. Oh, that's in milliseconds. Oh, of course. I've misread the original. I was assuming it's in seconds. Gosh, my fault. This is in milliseconds. Yeah, okay. So that's why. So it was right. So yeah, I'd misread that. So indeed, that is the correct step response, as it should be. That's time in seconds. That was in the milliseconds, this one, on the right, and time in seconds there. I said it would have a 30% overshoot. Well, it's got a 40% overshoot. But anyway, so what we're going to do now is design a controller for it to give a half-decent response. Now, in my book, I design using the phase advance, a phase lead. And I actually stick a second integrator in as well. So if we go to the board plot here, what you can do is you can add an integrator here at low frequencies, and then you can put a phase advance in here, and you can push the bandwidth up so that this resonance must be below 0 dB. You can read my book for the details here, but I'm going to, not everybody wants to design using lag lead controllers. A lot of people in industry just use PID controllers, and you kind of get the same. You should kind of get the same, answer. They're approximately the same. So I'm just going to ask it to do this. Normally I have to tune the damn thing in, or see here I'm actually will be designing it from the board plot, so I can calculate exactly what the controller is, and I can do that if I want to. But instead I'm going to get lazy, and I'm just going to say, can it work out a controller for me? So I'm going to say, instead of a constant gain for C of S, design a PID controller and give me the parameters to maximize the bandwidth of the closed loop system That's interesting, because as it pushes up the closed loop system bandwidth, it'll run into instability due to the resonance. So it'll probably have to run it quite a few times before it kind of gets the maximum. I just want to see what it comes up with. Show the closed loop step response. Now let's see it doing that. It says thinking, designing PID controller. It says frequency-based approach or methods like root locus. Actually, not many people use root locus. Maximize the bandwidth. Want to push the unity gain point near resonance. That's exactly right. Using PD action to flatten the response and apply. Well, that's exactly what I was going to do anyway. It's doing it kind of numerically. It'll be interesting to see what phase margin it comes up with. So that's all the things. So here it is doing some calculations in Python. It's running its own programming. Find indices where phase total crosses minus 120. So in other words, it's trying to get a phase margin of 60 degrees from what I can see. So it's an interesting way it's doing it. It's just kind of trial and error numerically. And it can do it, of course, it's because it's got brute force computing. We'd have to sit there and play around until we got it right. You notice it's taken a bit of time as well. It's not exactly trivial to do it. So it's iteratively going round. And it's working out. What's it doing there? Adjusting zeros for phase. And it's doing some more calculations, and so that's obviously no good. So I did pick this deliberately. So that's an unstable system. So it's checking the poles there by the looks of it. Now it's doing it again. You see, now that rings a bell. That one he's pushed the bandwidth too high up there, and that's the structural resonance that's happening, and they need to reduce the gain, overall gain. There we go. That's not bad. It's 20%. It's settled for a 20% overshoot. Actually, in my book, I managed to get 10% overshoot. So it's not exactly the best. Let's see. So this is a program that's going to run. What's this? Simulate it from to t equals 50 milliseconds. Where is it? Okay, I don't know what's happened. Replot the closed loop step response for these values. So again, it's created this program as it's running. There we go. Well, marks out of 10. It's not bad. It's not bad. And what's the bandwidth as it's produced? Oh, the maximum bandwidth of 400 radians. What's that? About 80 hertz or something like that. Yeah, I suppose it's not bad. What did I get? I did. I'm trying to look on my. I can't see it in 20. Yeah, it's not too bad. Quite reasonably fast. The overshoots though a bit on the big side. So, and how to deal with that would be to. I could even ask it to do that. I could ask it to, reduce the bandwidth a bit. To get the more phase shift, get less overshoot. Let's do that. Can you? reduce the overshoot to at least 10%, whilst maintaining, this is the tricky bit, the same bandwidth, or maintaining above. If necessary, introduce, that's spelling, if necessary, I've still spelled it wrong, but you'll know what I mean. If necessary, introduce a phase advance or other terms. Let it get on with that. It's a completely different approach, really, to doing it. I mean, I would have done that manually, but let it get on with it and do the hard work. It might not be that easy for it to do. Oh, of course. So that's the. So it's put a lead in, or phase advance. So it's trial and error again. Here's the. Tried a 15 degrees phase advance. Okay, I wouldn't have done that. I would have put in a 10 to 1, which is 55 degrees. Oh, that's more like it. Now we're talking. Now notice a little bit of that's the structural resonance. So the bandwidth slightly on the high side. We're getting ringing coming from the structural resonance. And that's more like it. So it's got a PID controller and a phase advance on top of it. That's like 1 plus, well, it's a bit like 1 plus ST1 over 1 plus ST2. That's your classic phase advance. So it's adding 30 degrees of phase advance. So it hasn't spotted the fact that it's got that, the effect of the structural resonance is still there. What I could do is ask it to reduce the gain slightly. But instead what I'm going to do is I'm going to just ask it to draw the open loop board plot for this latest design, and just have a quick look at it and see what it's actually done. It may be I can just reduce the gain slightly to get rid of the resonance. And the other things you could do is you could stick a low-pass filter in at the resonance, provided that low-pass filter's phase doesn't go down too far, and that will destabilize the system further. Here we go. Oh, it's done it, wrapped the phase again, which is really annoying. That's not bad though. So this is the gain margin here between 0 dB and that. That's about, oh gosh, what is that? About 10 dB or something. 10 dB of gain margin, something like that. Even 6 dB would be fine anyway. Maybe. This is the unity gain, the bandwidth of the system, and the phase margin is really good. It's actually 60 degrees. So it crosses over at minus 100. So it's 80 degrees minus 100. Yeah, difference between minus 100 and minus 180. 80 degrees. So does it say what the phase margin is? Extra 30 degrees. Okay. Phase margin. I'm just going to see if it knows what the phase margin is. What is the phase margin? It looks like 80 degrees to me. And gain margin. It might define the gain margin differently from me. But it depends. So it's actually going to work it out numerically, which is not, of course, we can just look at the board plot and get it off the board plot, but it's going to numerically work it out because, again, brute force. So it's index error. It's trying to find the phase. Might have difficulty with that. Wow. compute unwrapped phase. Phase margin 70 degrees, it says. I make it 80 degrees, but never mind. It's I would say it's 80, but if it's calculated exactly, it probably, it says gain margin of 16.7 dB, so that depends. Normally it depends how you define it. I'm defining gain margin as this difference between the peak here. But if it goes unstable before that reaches 0 dB, then it could be less than that. So let's just have a quick glance at it again. Unity gain is here, but 10 to 3, but here somewhere. Okay, yeah, I guess it's less than 80. It could be 70 something, because it's not quite at 100, is it? So yeah, that'll probably be right. Where does it say it again? Oh, there it is. Phase margin 69, 70 degrees. Yeah, I'd say it's 75, but okay, we can argue about that another day. That's not bad, is it? And we can get it to unwrap the phase if we so want to do that. So maybe I should ask it, okay, write the, suppose I'm happy with that. I'm not actually, but I suppose I was. Write down the transfer function of the controller, or for the controller of the controller. And in order to do that, it's having to program it. Oh, I think it's going to multiply it. It's going to multiply it all out into one. Oh God, I didn't want that. But oh, okay, no, that's all right. It's not too bad. There's the lead. There's the PID part. Doesn't seem to be any extra gain. It's absorbed the gain into that, so that there's no external K term in there. So action form that, and if you want to, we could even plot the board plot of the controller if you want to. I don't really see the point, but let's just do it. So just draw the board plot of the controller itself. Normally we don't do this. There's not a lot of point because it has to be combined with the system. But yeah, let's just get it to do it because we can. Shouldn't be too tricky to do it. Yeah, there it is. That's the controller. So it's an integrator and then this lead term. The phase closes off there. That's brought down later by the minus 40. Actually, it would be. It's a second order resonance, so it's minus 40 dB per decade roll off on the original. So the original board plot will be that'll be minus 20 dB per decade, and that'll be minus 20 minus 40, which is minus 60 dB per decade. And if you don't believe me, you can work it out from the slope of the decade. You can say from a decade's from 10 to the 5 to 10 to the 6. You can work it out from there. It's about 6, should be 80 dBs. Yeah, from about 100 to minus 180. So that's minus 8, and this should be minus 20 dB per decade. If you work that out. All confirming perfectly to theory. So there you go. That's how you can use ChatGPT to design. Well, this is classical control, but I'm sure if you use state space, you can do similar sorts of things. Notice the difference between this and what we were doing a few years back. Was it a year ago? I can't remember now. Where it just produced the code, and the code itself you had to run in a separate, application. Here it's doing everything itself. It's plotting everything. You can just instruct it to do various things. So here I end up with a final controller. So if I did indeed have this actual problem, and I was happy with that, which I say I'm not quite, because it's still got structural resonance in the step response. But if I was happy with it, I could implement this as a PID controller and a phase advance. That could be done in analog with a couple of op amps, and that's another phase advance, another op amp, and that's an integrator as well. Your integrator and the feedback path. You need quite a few op amps to do that. But anyway, that can be implemented. And I could even ask it. Might be interesting to see if it knows how would I implement that. I mean, of course, we could digitize that and do a digital implementation, which would be what we do anyway, because we'd be designing a digital compensator, not analog nowadays. But nevertheless, it's there kind of thing. I'll just say, how could I implement the controller? So I've spelt it all wrong. Implement the controller using operational. If you remember, it was never that good at operational amplifier, so I'm wondering if it's got any idea how to implement it. I'm sure even if it can't do it, I'm sure one day it will be able to do it. Yeah, it does got an idea. Split the control into two cascaded blocks. Yeah, PID block, and inverting summing amplifier that produces PID. Okay, you can get that. First order lead block, convenient values. Oh, it's actually gone into some detail. It's trying to draw me out. It's a shame about this. Maybe this will improve one day, and we'll get proper. It's hard to see, isn't it? The hell that is. Inverting op amp summer. Oh yeah, I see. That's that's a phase advance. It's got a resistor, capacitor, and a resistor in parallel. So that's a phase advance. Feedback path. It's got where's the feedback? I don't know where what it's got in the feedback path. Can't see that. This is using Mathematica or something here. It says Mathematica. Anyway, I think that's a bit crude. That reminds me of sort of 1970s ASCII style circuits, but I'm pretty sure it's going to improve. It's working out all the values. Course. See, it's working out all the values and doing it for me. Lead stage. I'd have to see a proper circuit diagram to make sure if that made sense. So knowing it's electronics from previous cases, it might be okay, but on the other hand, it might not be. But it's quite interesting that it's actually gone to all that trouble. Okay, thank you very much. Bye-bye.